Hello everyone. So this is a question from JEE Advanced 2026 paper 1. Considering LiBH4 reduces an ester group to the corresponding alcohol and does not reduce a carboxylic acid group, the correct statement about the major products P, Q, R and S is. Okay. So we start with this guy and we get P and Q. We start with this guy and we get R and S, and these are the options. The chapters involved is alcohols, phenols and ethers, aldehydes, ketones and carboxylic acid, and GOC. To get P and Q, we start with this guy. Okay, I can write this group as C double bond O, single bond O, ET is ethyl, so CH2, CH3, and I can write this group as C double bond O, OH. Okay, and this solid wedge represents above the plane of screen, and this dashed wedge represents below the plane of screen. Okay, so to get P, first we react this guy with LiBH4, which is lithium borohydride, and it is given that lithium borohydride selectively reduces ester group, that is this group, to corresponding alcohol. So this will be converted into a corresponding alcohol and does not reduce a carboxylic acid group. Okay, so therefore the original guy, that is this guy, will be converted to CH3, CH2OH, C double bond O and OH. Okay, then this guy is subjected to H plus, the second reagent, that is H plus. And remember, whenever a compound containing both COOH and OH is placed in an acidic H plus environment, it undergoes intramolecular esterification. Very important. To ultimately form cyclic ester. And cyclic esters are also known as lactones. Okay. So therefore, in a nutshell, H from OH and OH from COOH goes out in the form of a water molecule, and a new bond between O and C is formed. Okay, so therefore this guy in the presence of H plus will ultimately give us CH3, CH2O, C double bond O, and this. Okay, so this is our P. To get Q, we react our OG guy, that is this guy, with first reagent, that is BH3, which is borane. Okay, remember, when a carboxylic acid and an ester are both present in an organic compound, borane, that is BH3, selectively reduces the carboxylic acid to 1 degree alcohol, and it does not reduce the ester. Okay, it leaves the ester group entirely untouched. So I will write that down. Whenever you have a carboxylic acid and ester in the organic compound, BH3 converts this to 1 degree alcohol and does not have any action on the ester, and it leaves the ester group entirely untouched. Therefore, our original guy will be converted to CH3, C double bond O, O CH2 CH3, the ester group is intact. Then we have CH2 OH. Okay. Now this guy is subjected to the second reagent, that is H plus. Okay. Remember, when alcohol and ester are on the same molecular chain, they react with each other in an acid catalyzed process called trans-esterification. So the reaction between them is known as trans-esterification. Okay. In this, the alcohol group attacks the ester's carbonyl carbon, that is, this O will attack this carbon, okay, forming a cyclic ester. So in the end, we will again get a cyclic ester, which are, we know they are known as lactones. That is, with respect to reaction, I can, I will show it to you. So I will separate the H from O. Okay, so we know oxygen is more electronegative, so it will take away these electron pairs to form lone pairs. So it will have 3 lone pairs, 1 2 3 4 5 6, and it has a negative charge. Okay, then this oxygen will go and attack this carbon, which will bear a positive charge, and this oxygen will take away these electron pairs to form a lone pair. Okay, so we will get CH3 C O, and since this oxygen has taken these electrons, it will have 3 lone pairs now. So therefore there will be a negative charge, 1 2 3 4 5 6. Okay, and it is also attached to the OCH2CH3 group, and there is a new bond between this carbon and this oxygen, so which is CO and CH2 and O. Okay, in the next step, one of the lone pairs becomes a pi bond again, and this bond breaks. So we will ultimately get CH3 C double bond O, O, CH2 O. Okay, and this guy is our Q. So to determine the relation between P and Q, so let's look at them again. So we know what is Q. I will draw the structure of P again to compare. Okay, so P is CH3 CH2O C double bond O O. We should know that small cycloalkanes, for example, having 7 carbon and less, so those guys have restricted rotation about the CC bonds. For example, if you have cyclobutane, so there is rotation is not possible along this particular CC bonds or this particular CC bond. So these rotations are not possible, unlike our simple alkanes. In cycloalkanes, this bond rotation not possible. Okay, so therefore isomers exist which differ in orientation of groups on the ring. Okay, if the two groups are on same side of the ring, obviously, so they are known as cis, and if the two groups are on opposite side of the ring, then they are known as trans. Okay, for example, let's say I have cyclopropane and I have one CH3 above the ring, one below the ring, and let's say I have another cyclopropane where both the CH3 groups are above the ring. Okay, so since there is restricted rotation about this CC bonds, I cannot rotate this to get this. Okay, so therefore both of these are stereoisomers, that is, they have the same formula but different arrangement in space. Okay, and to be specific, they are geometric isomers. This one will be the cis form, this one will be the trans form. Okay. Now the same thing can be observed with P and Q. Okay. So this is our Q, this is our P. Okay. We simply cannot rotate the CC bond, that is, let's say this CC bond, and convert, either P to Q or Q to P. This is not possible because, as we have learned, in cycloalkane, CC bond rotations are restricted. Okay. Therefore, P and Q are geometrical isomers. Okay. And using rules, we can find out which one is E and which one is Z. And the most important thing is all the geometrical isomers are diastereomers. Very important. All geometrical isomers are diastereomers. That's because they are not mirror images of one another. Okay, so if you look at Q and P, they don't have any mirror image relationship with each other. So therefore, yes, Q and P are stereoisomers, and to be specific, they are geometrical isomers, and all the geometrical isomers are diastereomers. So therefore, P and Q are diastereomers. Okay. Okay. So now to get RNS, we start with this guy. Okay. And we are subjecting this guy to the same set of reagents, that is these guys. Okay. So from the previous discussions, R will be ring CH3 C double bond O, O CH2 O. And yes, I'm sorry, this will be S. R will be CH3 CH2 O C double bond O and O, and S will be CH3 C double bond O, O CH2. And using the same logic that we applied to P and Q, R and S are also diastereomers because CC bond rotation is restricted in cyclobutane. Okay, so therefore these guys are stereoisomers, or to be specific, they are geometrical isomers. Okay, we cannot convert P to Q, we cannot convert from P to Q by rotating it, as it is restricted, and all the geometrical isomers are diastereomers. So therefore the final answer is going to be C, that is P and Q are diastereomers and R and S are diastereomers. Okay, thank you.